Welcome to the first of two operations management tutorials on inventory models. Inventory models are especially important since every business uses inventory. Even small accounting firms keep a copier paper, toner cartridges, and the like in inventory. In this video, we will introduce the models, talk about several economic order quantity models, how to set the order quantity, and how to set the reorder point. In the second video, we will talk about fixed order interval models and single period models. My students can access the video tutorials for these problems using the content menu in D2L. YouTube viewers can access the video tutorials on my MOOC on udemy.com. I have a long and short version of the URL posted on the screen, and I will post this URL in the description. We're going to talk about three different types of inventory models in this tutorial. Two of these three different categories have multiple models in them. We'll talk about some of those. 1. Economic order quantity models. These are models where the order quantity is based on minimizing the cost of ordering and holding the inventory. We're going to talk about three of them: the Basic EOQ Model, 2. The Economic Production Quantity Model, and 3. The Quantity Discount Model. The second broad category we're going to look at are fixed order interval models, sometimes called fixed time period models. And number 3, single period models. Economic order quantity models are what are called event triggered. That is, something happens that causes you to place an order. Specifically, you monitor the inventory you have on hand, and when a reorder point is reached, you place an order. So if the reorder point is 50, you're monitoring the inventory. When it drops down to 50, you know it's time to place an order. A fixed time period model is time triggered. So for example, if you restock every Wednesday, the fact that Wednesday arrives triggers you placing an order. So you don't check inventory constantly, you don't monitor inventory constantly, you wait until Wednesday and check to see what you have on hand, or whatever day you do your ordering. These are the two most common sets of models, so let's compare them. In terms of average quantity on hand, the EOQ model tends to have lower average inventory. The reason for that, as we'll talk about in detail with the fixed time period model, is that there's less likelihood of a stock out. A stock out is where you run out of inventory. If you're always monitoring the inventory and placing an order when it gets down to 50, then you can't run out until after you reach 50 and place the order, because you have to go through 50 to get to 0. With a fixed time period model, say you're placing an order every Wednesday and it's coming in every Thursday. Well, when it arrives on Thursday, you can have a run on inventory and be completely out until next to Wednesday when you place the order, and then next Thursday when you receive that order. So in terms of chances of running out, as we've discussed, it's lower with the EOQ model and higher with the fixed time period model. In terms of number of orders that you place, you tend to place a higher number of orders with an EOQ model and a lower number of orders with a fixed time period model. Why is that? Well, when you have multiple items in inventory, you're counting each one with an EOQ system. So every time one drops below your order point, you order that one. And then the next one drops below the order point and you order that one. With a fixed time period model, Wednesday comes around, for example, and you order everything at once. In terms of safety stock is extra inventory that you carry to keep from running out. The higher your probability of running out, the more safety stock you're likely to carry. Since the chances of running out are higher with a fixed time period model, you're going to carry more safety stock. Since the chances are lower with an EOQ model, you're going to carry less safety stock. Now we're going to take a deep dive into 3 EOQ models. The first one will be the basic economic order quantity model. There are 6 assumptions. They are as follows. 1. Only one product is involved. That's a little misleading. It doesn't mean your business only has one inventory item. Rather, you calculate a different EOQ for every item in inventory. So each EOQ calculation you do only involves one product. 2. Annual demand requirements are known. This could be from a forecast or it could be from historical data, but the annual demand is an input to the calculation, so you have to either know it or have a good approximation of it for the EOQ model to work. 3. Demand is even throughout the year. It's not. We know that. The closer it is to even, the better the EOQ calculations are. The less even the demand is, the less useful the EOQ calculations are. 4. Lead times do not vary. In other words, if your lead time is 1 week, it's always 1 week. It's not 2 weeks now, 3 weeks then, 1 week now. 5. Each order is received in a single delivery. In other words, the vendor doesn't split up the shipment, send you part now, part later. Number 6. There is no quantity discount. In other words, you pay the same price no matter how much you order. We're going to look at 2 specialized EOQ models. In one, we're going to look at when the delivery comes in gradually, so we're going to violate assumption number 5. In the other, we're going to look at quantity discounts, which violates assumption number 6. The basic EOQ model has two parameters, R and Q, and we calculate both of them. R is the trigger point. That's the 50 in the example I gave you earlier. That's the point at which you place an order. So R is short for reorder point. Some textbooks will use ROP instead of R. Q is the quantity that you order. So when the on-hand drops to 50, say you order 400. Some textbooks use different symbols for Q. We'll talk about that in a moment. The graph on the screen shows the inventory cycle for the basic EOQ model. An order size Q comes in. With constant demand, on-hand inventory falls at a steady rate. We reach the point R, the reorder point, that's the 50. We place our order, but it doesn't come in right away, so average inventory continues to drop. We've timed our reorder point, so just as inventory drops down to 0, another shipment comes in and we go back up to level Q. And that just continues. The fewer orders we place means that each order is larger. So if you're using 1,200 a year, we can order 100 each month, or we can order 1,200 at the beginning of the year, or lots of other combinations. The fewer orders you place, the larger the order size, the larger Q, and therefore the higher average inventory is. We're placing fewer orders, so we're paying less in ordering cost. Order costs are related to buying the item, cutting a PO, purchase order, employee time, shipping costs. When we place more orders, each order is smaller, the 100 a month instead of 1,200 a year. That means we're placing more orders, and so the cost of placing the orders for the year goes up, but we've got less inventory. Therefore, inventory holding cost goes down. So when order cost goes up, average inventory goes down. When order costs go down, average inventory cost goes up. We're not trying to minimize either one of these. Instead, we're trying to find the point that minimizes the total of both of these. So we're trying to balance order cost with inventory holding cost. There are two different types of costs that we can calculate, and you have to be careful because different ones are used in different places. You also have to be careful to make sure that you're calculating the one that your textbook wants you to calculate. There's total cost. This is the cost of buying the inventory plus holding the inventory plus ordering the inventory. And then there's total cost of inventory, sometimes called total stocking cost. This ignores the purchase price. This is just the ordering cost plus the holding cost. You see two formulas on the screen. The first formula is total cost of inventory, also known as total stocking cost. Q over 2, that's the order quantity divided by 2. It's the average inventory. H is the annual holding cost for 1 unit of inventory. In other words, the cost of holding one item in inventory for 1 year. The combination of those terms gives us the inventory holding cost. Plus, D is annual demand. Q is the size of one order, so D divided by Q tells us how many orders we're going to place in a year, times S, the cost of placing one order. The second formula includes all those terms, but at the front it adds D times P. D is annual demand, remember. P is the price of 1 unit. That gives you the cost of actually buying the inventory for the year. Here's a hint on working these problems. If it gives you the price of 1 unit, you're probably supposed to use the second formula. If it doesn't give you the price of 1 unit, you can't use the second formula, so you have to use the first one. The basic EOQ formula to find the order quantity is the square root of 2 times the annual demand times the cost of placing one order divided by the holding cost expressed in dollars. It can't be a percentage. It has to be a dollar amount. Most textbooks call this Q star, which stands for the optimal order quantity. 1 or 2 textbooks will call it Q sub OPT, short for Q suboptimal. They mean the same thing. Now let's talk about a few notes on economic order quantity. Holding cost and ordering cost are usually estimated and rarely known exactly. In fact, I work for one company that used the same holding cost for every item in inventory. They just published an official amount. As a result, the Q value that you calculate is an approximate value. It's not an exact value. Also, small changes in the Q value have very little impact on cost. So you shouldn't do it on the homework problems, but in real life it's okay to round it to the nearest 10 or the nearest 100 or the nearest box size or the nearest pallet size, whatever makes sense for the item you're ordering. The economic production quantity is a special case of the EOQ model where production is done in batches or lots. It is almost always used when you're making the parts for yourself. So you're making cars, and in another factory or in another part of the same factory, you're making the engines. The economic production quantity model rarely makes sense when you're buying it from somebody else. The big assumption here is the capacity to produce a part exceeds the part's usage or demand rate. In other words, if you're making 500 cars a day, you've got the ability to make at least 500 engines a day, maybe a lot more. The assumptions of the economic production quantity model are the same as the EOQ model, except we're assuming that you receive the orders gradually or incrementally rather than all at once. In other words, they come in from the other factory in a truckload rather than all at once, or from the other part of the factory. If it's in the same factory, the engines might come in 10 or 20 at a time. So in net, the assumptions are 1, only one item is involved. 2, annual demand is known. 3, usage rate is constant. 4, usage occurs continually. 5, production rate is constant. 6, lead times do not vary. 7, no quantity discount. The model shown on the screen. When we start off, we're getting deliveries and we're using them at the same time. The engines are coming in and we're making cars. But the engines are coming in faster than we make cars, so inventory rises. The dotted line on the screen shows the production rate. The solid line shows the rate that the inventory on hand grows. So we're making the engines faster than we use them, so inventory is building up, but it's not building up as fast as we make them because we're using some of them as they come in. At some point, we've made enough engines to fulfill the order, so we stop making engines, but we're still using them, so the line turns around and goes down. And then the process starts over again when we need to order more. The economic order quantity is calculated as the square root of 2ds over h, which is the same as the basic EOQ, times the square root of P, the daily production rate, divided by P minus U, U being the daily usage rate. Some textbooks will put both of these under the same radical. That's fine. Maximum inventory, I sub max, is equal to my order quantity divided by my daily production rate times the quantity, my production rate, minus my daily usage rate. Average inventory is just my maximum inventory divided by 2. My total stocking cost is I max divided by 2 times H plus D divided by Q star times S. The only thing that changes is I'm swapping out the first Q for I sub max. And remember, I'm not showing you examples of these problems, but you have access to those in D2L if you're one of my students, or at my Udemy MOOC if you're not one of my students. Quantity discounts are price reductions for large orders offered to customers to induce them to buy in larger quantities. For example, you can bet that McDonald's pays less for hamburger buns than you do when you go to Kroger to buy some. That's simply because McDonald's buys a whole lot more hamburger buns than you do. Buying more than Q star raises your carrying costs since average inventory goes up. It lowers your order cost since you're placing fewer orders because each order is larger. It lowers your purchase price because you're paying less for each item. So my problem now is not how to minimize order cost plus holding cost. I know that's going to go up. The question becomes, is it worth spending more to hold the inventory in order to pay less to buy it? In other words, does the lower purchase price offset the higher total stocking cost? Remember, my aim is to minimize total cost, purchase price plus holding cost plus ordering cost. There are 2 different models that I have to consider. One where my carrying cost is constant, say $1 per item, and the other where my carrying cost is a percentage of the price. So if my carrying cost is a percentage of the price, my carrying costs go down when the price goes down. We're going to look at constant carrying costs first. In other words, I pay $1 per unit in carrying cost regardless of what the price is. The steps for solving this are as follows. 1. Compute the common minimum point. That is, find the Q value. Remember, price doesn't go in the calculations of Q. Carrying costs do, but if the carrying cost is constant, there's only one. Step 2. Only one price break will be feasible at that point. What do we mean by feasible? So if the price breaks are 0 to 50, 50 to 200, and 200 or above, if my order quantity is 75, then it's only feasible in that second category. In other words, I have to order more than Q to get into the third category. A, if the feasible minimum point is in the lowest price range, it is automatically the optimum order quantity and you don't have to do anything else. In other words, you're done with the problem. B, otherwise. In other words, it's not in the lowest price category. You have to compute the total cost at the minimum point for the feasible price break and all lower price breaks. Using the lower price breaks will require you adjusting Q. The most common mistake that I see students make in quantity discount problems is using the total stocking cost formula. You absolutely cannot do that. You will get the wrong answer. You have to use the total cost. In other words, you have to use demand times price. That is far and away the most common mistake that I see students make. Now let's talk about the EOQ procedures for percentage carrying costs. In other words, when the carrying cost varies based on the price that you pay for the item. Step 1. Beginning with the lowest price, compute the minimum cost point Q star for each price range. It'll be different for each price range because the holding costs go into the formula and holding costs depend on the price. In other words, you want to stop when Q is in a range that is allowable for that price range. You stop because Q will never be optimal in more expensive price categories. 2. If the minimum cost point for the lowest price is feasible, then it's optimal and you can stop. 3. Otherwise, compare the total cost at the price break equal to or lower than the feasible minimum. In other words, check the one where it's feasible and all the price breaks that are less expensive. You want to pick the one that has the lowest total cost, and remember we got to include annual demand and price in our calculations. You may not always take the quantity discount even if it saves you money. And in fact, in some scenarios, you may not even look to see if it makes sense to take the quantity price discount. Why is that? If you're buying items that will spoil, you have to hold them until they either sell or they spoil. If your demand is low enough that they're going to spoil before you sell the larger quantity, it doesn't make sense to buy the larger quantity. If you don't have enough storage room to store the extra quantity, it doesn't make sense. In fact, I know of some restaurants, at least before the pandemic, where when they would order stuff, they would order it to be delivered several times a day. That was more expensive, but they didn't have much storage space, so that was the only way they could keep the stuff that they needed on hand. If cash is tight, you might not be able to afford to buy the quantity, even if the quantity discount makes sense to you. Now let's talk about inventory models with planned shortages. I'm going to mention this briefly, but it's not mentioned in a lot of textbooks, so you may not encounter it. Sometimes customers are willing to wait. In other words, they're willing to tolerate stockouts. If that's the case, your inventory system can take advantage of that. An example of this might be a tire store selling high-performance tires or a high-fashion store selling some high-fashion item. In other words, a store selling something you're willing to wait for. So if you don't have to keep the item in inventory, you can only order it when the customer orders it. There's no inventory holding cost. If you do that, you've got to deal with your delivery dates, your promised delivery dates. They've got to be reasonable, and reasonable is in the customer's mind, not your mind. If you're a street racer looking for a high-performance tire, a week and a half might be reasonable. If you're an off-road pickup truck driver, it might not be reasonable. You've also got to strictly meet those deadlines or you're going to lose customers. Now let's talk about when to reorder. And these calculations apply to all of the 3 EOQ models we've talked about. First, let's talk about some terms. Reorder point, which we've talked about before, just as a reminder, when the quantity on hand of an item drops below this amount, the item is reordered. This was the 50 I talked about earlier. Safety stock, I mentioned that briefly as well. This is stock that is held in excess of expected demand due to variable demand rates and/or variable lead times. In other words, it's inventory that you're holding that you don't expect to use, but you're holding it just in case. Service level is the probability that demand will not exceed supply during lead time. So a 98% service level means that 98% of the time, you're going to have enough inventory to meet demand without stocking out, without running out. Why not make it 100%? Demand could be really high, and you don't want to carry that much inventory. It doesn't make sense to stock for extremes like that. So what determines the reorder point? 1, the rate of demand. The higher the demand, the higher the reorder point. If you use 1 a day and your lead time is 1 week, your reorder point is going to be 7. If you use 100 a day and a lead time of 1 week, your reorder point is going to be 700. Number 2, the lead time. The longer the lead time, the higher the reorder point. Likewise, the shorter the lead time, the lower the reorder point. This is one of the reasons that we might prefer local suppliers. 3, demand or lead time variability. The more variable demand is, or the more variable lead time is, the more safety stock we've got to carry to keep from running out, and therefore the higher the reorder point. 4, the stockout risk that's acceptable to management. A 98% service level directly implies a 2% chance of stocking out. If demand and lead time are constant, in other words, there's no variability, the reorder point, or OP, is just daily demand times the lead time in days, or weekly demand times the lead time in weeks. Doesn't matter what units of time you use, but both demand and lead time has to be expressed in the same units of time. When we have variable demand during lead time, or variable lead time, demand during lead time can be higher than we expect. It can also be lower than we expect, but you don't have a stock out when it's lower. In this case, we might want to carry additional inventory to reduce the chances of a stock out, in other words, to increase the service level. As I've mentioned, when we do that, it's called safety stock. When there's variable demand, the reorder point R is expected demand during lead time plus safety stock. In other words, to calculate the reorder point, we first must calculate safety stock. Safety stock is based on the service level. Service level is equal to 100 minus the stock out risk we're willing to tolerate. So a 2% stock out risk would yield 100 minus 2 equals 98% service level. Safety stock depends on 1, the average demand rate and average lead time, 2, the demand and lead time variability, and 3, the desired service level. When the expected demand during lead time and its standard deviation are known, the reorder point is equal to the expected demand during lead time plus Z times the standard deviation of the lead time. Z is the number of standard deviation units corresponding to your probability, and it's always a one-tailed probability because demand being too low doesn't lead to a stockout. Sigma sub LT is the standard deviation of the lead time. You have to be careful here. Sometimes problems will give you the daily standard deviation, and sometimes they will give you the standard deviation during lead time. If they give you the standard deviation during lead time, you're fine. You just plug it into the formula. If they give you daily standard deviation, you have to convert it to standard deviation during lead time. The conversion is the standard deviation during lead time is equal to the square root of lead time times this daily standard deviation. You have to pay attention to the wording of the problem to know if you need to make this conversion or not. Sometimes data on lead time demand are not readily available. That means you can't use the formulas I've been showing you. Generally, however, data is available on average demand and average lead time. You can use that data to approximate the standard deviation and the lead time. When only demand during lead time is variable, the reorder point R is daily demand times the lead time in days plus Z times the standard deviation during lead time. When only lead time is variable, the reorder point R is equal to daily demand times the average lead time plus Z times the daily demand times the standard deviation of lead time. When they're both variable, the reorder point D is equal to the average daily demand times the average lead time plus Z times the square root of the average lead time times variance of demand plus D squared times the variance of the lead time. When demand is variable, we use the average demand, and when lead time is variable, we use the average lead time in these formulas. We will pick up our discussion of the fixed order interval model in the next tutorial. If you enjoyed this video, please click like and consider subscribing to this channel.